What if rockets didn't burn fuel, but used nuclear reactions? It sounds like science fiction, but it is a real idea that scientists have seriously considered. Every rocket you have ever seen works in a simple way. It burns fuel, creates hot gas, and throws it out the back to move forward. But hidden inside that simple idea is a problem most people never notice. The farther you want to go, the more fuel you must carry. And the more fuel you carry, the heavier your rocket becomes. And that extra weight means you need even more fuel just to move. It becomes a loop that is incredibly hard to escape. This is one of the main reasons why traveling to places like Mars is still so difficult and so slow. But there is another way, a completely different way, one that does not rely on chemical burning at all, but instead taps into a form of energy millions of times more powerful. If that is true, then everything we think we know about space travel might be about to change forever. When most people think about rockets, they imagine power, I fired, and raw force pushing a machine into space. And in a way, that image is correct, because rockets really do rely on burning fuel to create thrust. But hidden beneath that dramatic image is a much deeper problem, one that quietly limits everything we try to do in space. The problem is not just how powerful rockets are, but how inefficient they become the moment we try to go farther. A rocket does something very strange compared to almost any other vehicle, you know. A car pushes against the road. A plane pushes against the air. But a rocket has nothing to push against in space. So it must carry everything it needs with it, both the fuel and the reaction mass that it throws out the back. This means that from the very beginning, a rocket is burdened by its own fuel, and that creates a fundamental challenge. Imagine you want to send a spacecraft to Mars. You might think the main challenge is building an engine powerful enough to get there, but in reality, the bigger challenge is carrying the fuel required for the journey. To accelerate in space, you need to throw mass backward. The more you want to speed up, the more mass you must throw away. And that mass is your fuel. But here's where things start to become counterintuitive. To carry more fuel, you need a bigger rocket. But a bigger rocket weighs more. And because it weighs more, it now requires even more fuel just to lift itself. And that extra fuel adds even more weight. So you add more fuel again. And again, very quickly, you find yourself trapped in a loop where most of your rocket is not payload, not astronauts, not scientific instruments, but just fuel needed to carry more fuel. This is why rockets look the way they do. When you see a rocket on a launch pad, almost the entire structure is fuel tanks. The actual payload at the top is tiny compared to the massive body below it. In many cases, more than 90% of the rocket's mass is just fuel. That is not because engineers are inefficient. It is because physics forces them into this design. And the deeper you go into this problem, the more extreme it becomes. If you want to go just a little faster, you do not need just a little more fuel. You need exponentially more. Each increase in speed requires disproportionately more fuel than the last. So missions that seem only slightly more ambitious can suddenly become dramatically more difficult. This is the hidden problem with rocket fuel. It creates a kind of compounding burden. Every kilogram of fuel you add increases the amount of fuel you need. Every improvement you try to make is weighed down by the cost of carrying it. It is like trying to run while carrying a backpack that keeps getting heavier the more you try to prepare for the journey. And this is why traveling to distant places in space is so challenging. Getting to orbit around Earth is already difficult. But going beyond that, to the moon, to Mars, or even farther, requires dealing with this growing wall of fuel requirements. It is not just a question of building a stronger engine. It is a question of escaping a system where the solution makes the problem worse. So even though rockets have taken humans to the moon and sent probes across the solar system, they are still fundamentally limited by this hidden constraint. Chemical fuel gives us a certain amount of energy. And no matter how much we refine our engineering, we cannot escape the fact that we must carry that energy with us as mass. And that leads to a deeper realization. The problem is not just engineering. It is the kind of energy we are using. As long as we rely on chemical reactions, we are stuck within a narrow range of efficiency. And as long as we are stuck in that range, the dream of traveling faster and farther will always come with an enormous cost. At first, it might seem like the problem with rockets is just a matter of better engineering. Build stronger materials, design more efficient engines, optimize fuel mixtures, and eventually we will overcome the limits. But the deeper truth is more uncomfortable. Chemical rockets are not just limited by technology. They are limited by physics itself. No matter how advanced we become, there is a ceiling we cannot break as long as we rely on chemical reactions. To understand why, we need to look at what a chemical rocket actually does. Inside the engine, fuel and oxidizer react, breaking and forming chemical bonds. This process releases energy, which heats up the exhaust and pushes it out at high speed. That exhaust velocity is what determines how effective a rocket is. The faster you can throw mass backward, the more efficiently you can move forward. But here is the key limitation. Chemical energy comes from the rearrangement of electrons in atoms, not from the nucleus itself, and the amount of energy stored in chemical bonds is relatively small. It is powerful enough to launch rockets off Earth, but it is tiny compared to the energy stored inside atomic nuclei. This means that even the best possible chemical fuel has a hard upper limit on how much energy it can release per kilogram. Engineers have already pushed chemical propulsion very close to that limit. Modern rocket engines are incredibly optimized. They burn fuel at extremely high temperatures, use advanced materials to withstand stress, and are designed to squeeze out every bit of performance possible. But despite all of that, the improvement over the past decades has been incremental, not revolutionary. The reason is simple. You cannot engineer your way past the fundamental energy density of chemical bonds. This creates a ceiling on something called exhaust velocity, which directly controls how efficient a rocket can be. If your exhaust cannot move faster, your rocket cannot become dramatically more efficient. And if your efficiency cannot improve, then the fuel problem you saw earlier does not go away. It just becomes a permanent constraint. Now imagine trying to design a mission to Mars using only chemical rockets. You already know that fuel dominates the mass of the rocket. But because your efficiency is capped, the amount of fuel required grows very quickly as you try to increase speed or carry more payload. This is why missions to Mars take many months. It is not because we do not want to go faster. It is because going faster would require an impractical amount of fuel. And this is where the situation becomes almost paradoxical. We have incredibly advanced rockets built with cutting-edge technology, guided by precise physics. Yet they are still trapped within a narrow performance window. It is like having a car engine that is already operating near the maximum efficiency allowed by the laws of chemistry. No matter how much you refine it, you cannot suddenly turn it into something fundamentally more powerful. So the real barrier is not that we have not tried hard enough. The barrier is that chemical rockets are based on a form of energy that is simply too weak for the scale of the universe we want to explore. Space is vast. Distances are enormous. And the energy required to move quickly across those distances grows beyond what chemistry can reasonably provide. This is why, for decades, scientists have been forced to accept a trade-off. You can go far, but slowly, or you can go faster. But at the cost of carrying enormous amounts of fuel, there is no easy way out within the framework of chemical propulsion. And once you see this clearly, a new question naturally emerges. If the limitation comes from the type of energy we are using, then maybe the solution is not to improve rockets, but to change the energy source entirely. At some point, engineers and physicists began to realize something important. If the limitation of rockets comes from the kind of energy we use, then improving engines is not enough. You do not solve the problem by making chemical rockets slightly better. You solve it by changing the source of energy entirely. And that is where a radical idea enters the picture. An idea that sounds extreme at first, but becomes surprisingly logical the more you think about it. Instead of relying on chemical reactions, what if we use nuclear energy to power rockets? To understand why this idea is so powerful, you have to step back and compare the two types of energy. Chemical reactions involve electrons moving between atoms, forming and breaking bonds. Nuclear reactions, on the other hand, involve the nucleus itself, the core of the atom. And the difference in energy between these two processes is enormous. A single nuclear reaction can release millions of times more energy than a chemical reaction involving the same amount of mass. That is not a small improvement. That is a completely different scale. This realization changes the entire perspective on space travel. The problem we saw before was that rockets must carry their energy as fuel. And that energy was limited. But if each kilogram of fuel could store far more energy, then suddenly the balance begins to shift. You would not need to carry nearly as much mass to achieve the same effect. The loop of adding more fuel to carry more fuel starts to weaken. At first, the idea of a nuclear rocket might sound dangerous or even absurd. Many people immediately imagine explosions, radiation, or something unstable. But that intuition comes from thinking about nuclear weapons, not nuclear propulsion. The goal here is not to create an explosion. The goal is to use nuclear reactions in a controlled way, just like in a power plant, to produce heat. And heat, in the context of a rocket, is exactly what you need. This is where the idea becomes surprisingly simple. A rocket engine does not actually care how heat is produced. It only cares that something gets very hot and expands rapidly out the back. In a chemical rocket, burning fuel creates that heat. In a nuclear rocket, a reactor could create that heat instead. The mechanism of thrust stays the same, but the source of energy changes completely. This shift opens the door to a new class of propulsion systems that were once seriously studied, especially during the early days of the space race. Scientists began exploring designs where a nuclear reactor would replace the combustion chamber of a traditional rocket. Instead of burning fuel, the reactor would generate intense heat continuously without the need for chemical combustion. This heat could then be used to accelerate a propellant, pushing it out of the engine to create thrust. What makes this idea so compelling is not just that it works in theory, but that it directly targets the core limitation of chemical rockets. By increasing the amount of energy available per unit of mass, you fundamentally change how efficient a rocket can be. The entire balance between fuel, payload, and performance starts to shift in a way that was previously impossible. And this is why nuclear propulsion has always been seen as one of the most promising paths for deep space exploration. It is not just an upgrade. It is a transition to a different level of capability. Instead of being trapped within the narrow limits of chemistry, you begin to tap into the much deeper energy stored inside matter itself. Once you accept this idea, the next step becomes inevitable. If nuclear energy can provide vastly more heat than chemical reactions, then how exactly would a rocket use that heat to move through space? The answer turns out to be far simpler than most people expect. And that simplicity is what makes the concept so powerful. Once you accept the idea that nuclear energy can replace chemical burning, the next question becomes very simple. How does a nuclear rocket actually work? And the surprising answer is that it works almost the same way as a normal rocket, just with a different source of heat. There is no explosion pushing the spacecraft forward, no constant detonation, no uncontrolled reaction. Instead, everything is based on a controlled flow of heat and expanding gas. At the center of a nuclear thermal rocket is a small nuclear reactor. This reactor does not explode like a bomb. It operates steadily, like the reactors used in power plants, but designed to be much more compact and much more powerful for its size. Inside the reactor, nuclear fuel undergoes fission, releasing an enormous amount of heat. This heat is the key to everything that follows. Now, instead of burning fuel to create hot gas, the rocket carries a separate propellant, usually something very light like hydrogen. This hydrogen is not burned. It is pumped through the reactor, where it passes over or through extremely hot reactor elements. As it flows through, it absorbs heat, and its temperature rises dramatically. When hydrogen gets this hot, something important happens. It expands. Its molecules move faster, and it becomes a high-energy gas. And just like in a chemical rocket, that hot gas is then forced out of a nozzle at the back of the engine. The nozzle is shaped in a way that converts thermal energy into directed motion, accelerating the gas to extremely high speeds as it exits. This is where thrust is created. The rocket pushes mass out the back, and in response, it moves forward. The physics is exactly the same as any other rocket. The only difference is how the gas got hot in the first place. In a chemical rocket, heat comes from combustion. In a nuclear thermal rocket, heat comes from the reactor. And this difference turns out to be extremely important because the reactor can reach much higher temperatures than chemical combustion. The hydrogen can be heated to much higher energies. That means it can be expelled at much higher speeds. And higher exhaust speed directly translates into better efficiency. Another subtle but important advantage comes from the choice of hydrogen itself. Hydrogen is the lightest element, which means for a given amount of energy, it can reach very high velocities when heated. This makes it an ideal propellant for maximizing performance. You are not just using a more powerful energy source, you are also using a propellant that responds exceptionally well to that energy. The entire system is, in a sense, elegantly simple. A reactor produces heat. A fluid carries that heat, and a nozzle converts it into motion. There are no flames in the traditional sense, no need for mixing fuel and oxidizer, and no dependence on chemical reactions at all. This simplicity is part of what makes the concept so appealing to engineers. Of course, simple does not mean easy. The materials inside the reactor must withstand extreme temperatures and radiation. The system must remain stable under intense conditions. and it must be lightweight enough to function as part of a spacecraft. These are serious engineering challenges, but none of them violate the laws of physics. They are difficult problems, not impossible ones. And when you step back and look at the whole design, something becomes clear. A nuclear thermal rocket is not a completely alien technology. It is an evolution of the same basic principle that rockets have always used, just powered by a far more intense source of energy. It takes the familiar idea of heating gas and pushing it out the back, and amplifies it to a level that chemical systems simply cannot reach. This is why. Once people understand how it works, the idea feels less like science fiction and more like an obvious next step. If you can generate more heat, you can move faster. And if you can move faster using less propellant, you begin to break free from the limitations that have defined space travel for decades. At this point, the idea of a nuclear thermal rocket might already seem impressive, but the real reason it matters comes down to one key question: how efficient is it? Because in space travel, efficiency is everything. It determines how fast you can go, how much you can carry, and how far you can travel before running out of propellant. And this is where nuclear rockets begin to separate themselves in a very clear way. To understand this, we need to go back to a simple idea. A rocket works by throwing mass out the back. The faster that mass is thrown, the more push the rocket gets in return. This is not just about force. It is about how effectively you are using the propellant you carry. If you can get more speed out of each kilogram of propellant, then you need less of it overall. Chemical rockets are limited in how fast they can throw that mass. The speed of their exhaust depends on how much energy is released when fuel burns. But as we saw earlier, chemical reactions only release a relatively small amount of energy per unit of mass. This puts a hard cap on exhaust velocity. Even the best chemical engines in the world can only push exhaust so fast before they reach their physical limits. A nuclear thermal rocket changes that balance completely because the heat comes from nuclear reactions. The amount of energy available is far greater. This allows the hydrogen propellant to reach much higher temperatures than any chemical combustion process could safely achieve. And higher temperature means higher exhaust speed. This is why nuclear thermal rockets are often described as being about twice as efficient as chemical rockets. In technical terms, this is measured by something called specific impulse, which is essentially a way of describing how much thrust you get per unit of propellant. But you do not need the technical definition to understand the impact. What matters is that for the same amount of propellant, a nuclear rocket can produce much more motion. Think of it this way. If two rockets carry the same mass of propellant, but one can throw that propellant out twice as fast, then it can achieve a much higher final speed. Or, if both rockets need to reach the same destination, the more efficient one can carry, less propellant and more useful payload instead. In both cases, the advantage compounds over the entire mission. And this is where things become powerful in a way that is not immediately obvious. The improvement is not just linear. Because of the way rockets work, small increases in efficiency lead to disproportionately large improvements in overall performance. This means that doubling efficiency does not just make missions twice as good. It can make entirely new missions possible. For example, a journey to Mars with chemical rockets requires a very careful balance between fuel, payload, and travel time. Missions often take many months because accelerating faster would require too much propellant. But with a nuclear thermal rocket, the higher efficiency means you can achieve greater speeds without dramatically increasing fuel mass. This opens the possibility of shorter travel times and more flexible mission design. There is also another hidden benefit, because you need less propellant for the same mission. The total mass of the spacecraft can be reduced, and as you saw earlier, reducing mass helps break the cycle where more fuel requires even more fuel. This creates a cascading effect where improvements in efficiency simplify the entire system. In a sense, nuclear thermal propulsion attacks the problem at its root. Instead of trying to optimize within the limits of chemistry, it steps outside those limits and uses a form of energy that is inherently more concentrated. That is why the improvement is so significant. It is not a small engineering tweak. It is a shift in the underlying physics that powers the system. And once you understand this, it becomes clear why scientists have been interested in this technology for so long. If you can get more speed from less propellant, you are no longer as tightly bound by the constraints that have defined space travel for decades. You begin to open up a new range of possibilities. But that leads to an even more important question. If nuclear rockets are so much more efficient, what does that actually change when it comes to real missions? Especially something as ambitious as sending humans to Mars. Once you understand that nuclear thermal rockets can deliver much higher efficiency, the next question becomes very practical. What does this actually change for real missions? Especially something as difficult as sending humans to Mars. Because in space travel, improvements are only meaningful if they translate into real advantages. Shorter travel time, lower risk, and greater mission flexibility. And this is where nuclear propulsion begins to reshape the entire picture. With chemical rockets, missions to Mars are tightly constrained by physics. Space agencies must carefully choose launch windows when Earth and Mars are aligned in a favorable way. Even then, the journey typically takes around 6 to 9 months. This is not because engineers prefer it that way, but because going faster would require an enormous increase in fuel, which quickly becomes impractical. So instead of accelerating hard and arriving quickly, spacecraft follow energy-efficient paths that trade speed for feasibility. But long travel time introduces a series of problems that go far beyond inconvenience. For astronauts, months in deep space means continuous exposure to cosmic radiation. Earth's magnetic field no longer protects them, and over time, this radiation increases the risk of serious health effects. The longer the journey, the greater the accumulated exposure. There is also the issue of microgravity. Spending months without gravity affects the human body in significant ways. Muscles weaken, bones lose density, and the cardiovascular system adapts in ways that can make returning to a planetary surface more difficult, even with exercise and countermeasures. The effects cannot be completely eliminated. Reducing travel time directly reduces these risks. Then there is the psychological dimension. A mission to Mars is not just physically demanding, it is mentally challenging. Astronauts would spend months in a confined environment, far from Earth, with limited communication and no possibility of quick rescue. The longer the mission duration, the greater the strain on mental health and team dynamics. Shorter missions are not just safer physically, they are easier to manage psychologically. This is where nuclear thermal rockets offer a critical advantage. Because they can achieve higher exhaust velocities, they can accelerate spacecraft more efficiently. This means that instead of relying solely on slow, energy-saving trajectories, missions could use faster transfer paths. In practical terms, this could reduce travel time to Mars significantly, potentially cutting months off the journey. And the benefits do not stop there. Higher efficiency also means more flexibility in mission design. With chemical rockets, every kilogram is tightly budgeted, adding extra shielding. Additional supplies or redundant systems can quickly become too costly in terms of mass. But with a more efficient propulsion system, that constraint begins to loosen. Spacecraft could carry more protection against radiation, more life support resources, or additional scientific equipment without exceeding launch limits. Another important change comes from how missions are planned. Currently, Mars missions depend heavily on narrow launch windows that occur roughly every 26 months. Missing one of these windows can delay a mission by years. But with more powerful propulsion, spacecraft are less dependent on perfectly optimized trajectories. This could open up more flexible launch opportunities and reduce the risk of costly delays. There is also the possibility of more complex mission profiles. Faster travel times and higher efficiency could allow for missions that include faster return trips, or even multiple destinations within a single mission architecture. What was once considered too ambitious could become realistic with the right propulsion system. In a broader sense, nuclear thermal rockets do not just make existing missions better. They expand what is possible. They move Mars missions from the edge of feasibility towards something more practical and sustainable. Instead of being rare, high-risk endeavors, they could become more routine over time. And this is why the idea has remained so compelling for decades. It offers a way to solve not just one problem, but many of the challenges that have always made human exploration of Mars so difficult. It reduces travel time, lowers risk, increases flexibility, and improves overall mission design. But this brings us to a question that is hard to ignore. If a technology exists that can make Mars missions safer, faster, and more practical, then why are we still not using it today? By this point, the picture seems almost too clear. We have a propulsion system that is more efficient, capable of reducing travel time, lowering risk for astronauts, and making missions to Mars more practical. The physics works. The engineering has been studied for decades, and the potential benefits are undeniable. So a natural question begins to surface, one that is both simple and uncomfortable. If nuclear thermal rockets are so promising, why are we not using them today? At first, you might expect the answer to be purely technical. Maybe the technology is not ready, or the reactors are too unstable, or the materials cannot handle the extreme conditions. But the truth is more complicated than that. The challenges are not just about physics or engineering. They are also about fear, politics, and the way humans respond to risk. The word nuclear carries a heavy weight. For many people, it immediately brings to mind images of bombs, disasters, and long-term contamination. Even though a nuclear rocket is fundamentally different from a weapon, the association is hard to escape. Launching something powered by a nuclear reactor from Earth creates a psychological barrier that goes far beyond technical concerns. People do not just evaluate the probability of failure. They imagine the consequences if something goes wrong. And that leads to one of the biggest concerns. What happens if a rocket carrying a nuclear reactor fails during launch? Rockets do fail. Not often, but often enough that engineers must always plan for it. If a chemical rocket explodes, the result is dramatic but localized. But if a nuclear-powered rocket were to break apart in the atmosphere, the fear is that radioactive material could be spread over a wide area. Even if the actual risk can be managed or minimized through design, the perception of that risk is extremely difficult to overcome. Because of this, governments and space agencies must consider not only what is technically possible, but what is publicly acceptable. A single accident involving nuclear material could have consequences that go far beyond the immediate event. It could trigger political backlash, international tension, and long-term damage to public trust in space programs. There are also legal and regulatory challenges. Launching nuclear material into space involves strict international agreements and safety protocols. These frameworks are designed to prevent harm, but they also make development and testing far more complex and expensive. Every step must be carefully reviewed, every risk analyzed, and every decision justified at multiple levels. This slows down progress and increases the cost of pursuing nuclear propulsion. Cost itself is another major factor. Developing a nuclear thermal rocket is not just about building an engine. It requires designing compact reactors, testing them safely, creating specialized infrastructure, and ensuring long-term reliability. These are expensive and time-consuming efforts. And in a world where budgets are limited, space agencies often prioritize projects that are less controversial and more immediately achievable. There's also a historical reason behind the delay. During the early space race, nuclear propulsion was actively researched, and real prototypes were tested. But as political priorities shifted and funding changed, many of these programs were canceled before they could reach full deployment. The momentum was lost, and with it, decades of potential progress. Perhaps the most subtle reason is that chemical rockets, despite their limitations, still work well enough for current missions. They can launch satellites, send probes, and even support plans for Mars exploration, albeit slowly and at high cost, because there is already a working system in place. The urgency to replace it is not always strong enough to justify the risks and investments required for nuclear propulsion. So the situation we find ourselves in is not one where nuclear rockets are impossible. It is one where they exist in a kind of tension between what we can do and what we are willing to do. The physics allows it. The engineering supports it. But human concerns, political realities, and risk perception hold it back. And this reveals something deeper about space exploration. The limits we face are not always written in the laws of physics. Sometimes they are shaped by the decisions we make, the risks we accept, and the fears we cannot easily overcome. When you look deeper, the reason nuclear thermal rockets are not in use today is not a single problem, but a combination of forces that reinforce each other. It is not just about safety or cost or politics alone. It is the interaction between all of them that creates a barrier difficult to overcome. And to understand this clearly, you have to move beyond the surface level concerns and look at how these factors actually shape decisions over time. One of the most important factors is timing. Nuclear propulsion was seriously developed during a very specific period, the early space race, when there was intense political pressure to achieve breakthroughs quickly. During that time, large scale, high-risk projects were more acceptable because they were tied to national prestige and competition. Programs were funded aggressively, and engineers were given the freedom to explore bold ideas. Nuclear rocket engines were not just theoretical. They were built and tested, and the results showed that the concept could work. But then the world changed. After the moon landing, the urgency that had driven these efforts began to fade. Public interest shifted, political priorities moved elsewhere, and funding for ambitious space technologies was reduced. Without that strong external pressure, nuclear propulsion lost its momentum. It was not abandoned because it failed. It was set aside because it was no longer seen as immediately necessary. At the same time, the perception of nuclear technology itself was changing. As more people became aware of nuclear accidents and long-term environmental risks, public sensitivity increased. Even peaceful uses of nuclear energy began to face stronger scrutiny. In this environment, proposing to launch nuclear reactors into space became much more controversial. The risk did not have to be high to be unacceptable. It only had to be visible. This created a feedback loop. Because nuclear propulsion was controversial, it became harder to secure funding and political support. Because it lacked funding, development slowed down. And because development slowed down, the technology never reached the level of maturity needed to prove its full potential in real missions. The longer this cycle continued, the more distant the ideas seemed. There is also a structural challenge in how space programs operate today. Large-scale projects require international cooperation, long-term planning, and consistent funding across many years. Introducing a technology that carries additional regulatory complexity and public concern makes coordination even more difficult. It is often easier to continue improving existing systems than to take on the uncertainty of something entirely new. Another key issue is infrastructure. Chemical rockets benefit from decades of development, established supply chain, and well-understood launch systems. Everything from fuel production to launch procedures has been refined over time. Nuclear thermal rockets would require a different kind of support system, including facilities for handling nuclear materials, specialized testing environments, and new safety protocols. Building this infrastructure is a major investment, and it must happen before the technology can be widely used. There is also the challenge of risk distribution. The benefits of nuclear propulsion are long-term and often shared globally, such as advancing human exploration or enabling deeper space missions. But the risks, especially during launch, are local and immediate. This imbalance makes decision-making more complicated. Communities near launch sites may be more concerned about potential accidents than about the distant benefits of faster Mars missions. And perhaps most importantly, there is the question of necessity. As long as current technology can achieve mission goals, even if imperfectly, there is less pressure to adopt something more controversial. Chemical rockets may be inefficient, but they are reliable, understood, and politically acceptable. This creates a kind of inertia where the existing system continues, not because it is ideal, but because it is good enough. When you put all of these factors together, a pattern emerges. Nuclear thermal rockets are not being held back by a single technical limitation. They are held back by timing, perception, infrastructure, cost, and the absence of urgent demand. Each of these factors alone might be manageable, but together they create a barrier that is difficult to break. And this leads to a deeper realization. The future of space travel is not determined only by what is possible, but by what we choose to pursue. Nuclear propulsion represents a path that could change how we explore the solar system. But taking that path requires more than scientific understanding. It requires willingness, coordination, and a shift in how we think about risk and progress.